December 17th, 1944. Heeresversuchsstelle Kummersdorf, Brandenburg, Germany. Dr. Heinrich Klein's hands trembled as he lifted the metal shell fragment from its cushioned examination tray, studying what would become known as the most profound revelation in German ordnance development. The device, no larger than a man's fist and weighing barely 200 grams in its shattered state, contradicted everything German engineers had calculated about miniaturized electronics and mechanical precision. This cannot function at artillery velocities. Our calculations proved such miniaturization impossible under combat acceleration forces. 48 hours earlier, American artillery had pounded German positions near Aachen during the grinding advance toward the Rhine. Among the thousands of shells fired, one had malfunctioned spectacularly, detonating prematurely above German lines but failing to cause casualties. Wehrmacht recovery teams, trained to salvage unexploded ordnance for intelligence analysis, found fragments of the shell scattered across frozen ground. What they discovered would force German leadership to confront a technological achievement so far beyond their capabilities that it seemed almost magical in its sophistication. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. The story of Germany's encounter with the proximity fuse began not with a single captured shell, but with mounting evidence throughout 1943 and 1944 that Allied anti-aircraft fire had become unnaturally effective. Luftwaffe bomber crews returning from missions over Allied-controlled territory reported flak bursts that seemed to track aircraft with impossible accuracy. Shells were exploding not upon impact or at predetermined altitudes, but at precisely the moment they passed closest to aircraft. Fighter pilots described curtains of explosions forming around their planes, as if the shells themselves could sense their presence and detonate at optimal kill range. Initially, German air defense analysts dismissed these reports as combat stress or exaggeration. Flak always seemed more accurate to those being shot at. Pilots under fire naturally overestimated enemy capabilities. But as reports accumulated from multiple fronts, from experienced crews, from officers whose observations carried credibility, German intelligence began taking the accounts seriously. Something had changed in Allied anti-aircraft effectiveness that conventional explanations could not account for. The mathematical improbability of what was being described troubled German ordnance specialists deeply. Traditional anti-aircraft shells used time fuses, mechanical or powder train devices set before firing to detonate at calculated altitude based on estimated target height and speed. Accuracy required precise ranging, exact timing calculations, and assumptions about target behavior that were often wrong. Even the best flak batteries achieved hit rates measured in fractions of 1%. Thousands of shells might be fired to achieve a single aircraft kill. The process was fundamentally inefficient, a statistical game where volume of fire compensated for individual shell inaccuracy. Yet Allied anti-aircraft fire in 1944 was achieving hit rates that suggested something fundamentally different was occurring. Shells were not being fired in the traditional pattern of predicted barrage, but seemed to be responding to actual aircraft position in real time. The accuracy suggested individual shells possessed some form of target sensing capability, an idea that seemed preposterous given the limitations of miniaturization German engineers understood. Dr. Werner Osenberg, heading the planning office of the Reich Research Council, received reports throughout 1944 describing unexplained Allied capabilities, anti-aircraft shells detonating at optimal range without apparent time fuse settings, naval bombardment achieving accuracy that exceeded visual range-finding capabilities, artillery barrages landing with consistency that suggested guidance systems German technology could not duplicate. Each report added pieces to a puzzle that Osenberg and his colleagues struggled to solve. What technology could Allied forces possess that German intelligence had completely missed? German scientists were acutely aware of their own limitations in miniaturized electronics. Radio tubes required careful mounting to survive even modest shock and vibration. Precision mechanical components failed under sustained acceleration. Miniaturizing electronics, small enough to fit inside artillery shells, while surviving forces of 30,000 times gravity during firing seemed impossible based on German experience. The forces involved during shell launch were extraordinary. When a 105mm shell left the gun barrel, internal components experienced acceleration forces that would instantly destroy any radio tube German industry could manufacture. Vacuum tubes required glass envelopes that shattered under such stress. Filaments snapped. Connections failed. Even if electronics could somehow survive the launch, they would need to function while spinning at hundreds of revolutions per second as the shell rotated for stability. German engineers had attempted to develop guided projectiles, but had abandoned artillery shell applications as technically infeasible given these constraints. The evidence suggested Allied engineers had solved problems German specialists considered insurmountable. Throughout late 1943 and into 1944, Luftwaffe losses to anti-aircraft fire climbed steadily in all theaters. Over Germany itself, American bomber formations faced increasingly effective flak as they penetrated deeper into the Reich. But, over Allied-controlled territory, German aircraft faced anti-aircraft fire of unprecedented lethality. The asymmetry was striking and unexplained. German flak remained effective against Allied bombers when employing traditional barrage tactics, yet Allied anti-aircraft achieved hit rates against German aircraft that seemed impossible with conventional time-fused ammunition. Fighter sweeps over Normandy after D-Day encountered flak curtains that seemed almost prescient, shells exploding at precise moments as aircraft maneuvered through defensive patterns. Experienced pilots who had survived years of combat reported they had never encountered anti-aircraft fire so consistently accurate. Something had changed in the fundamental nature of anti-aircraft warfare, and German intelligence struggled to understand what Allied technology made it possible. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. In September 1944, German intelligence received its first substantial clue. A Kriegsmarine minesweeper, operating in the English Channel, recovered shell fragments from what appeared to be an Allied naval bombardment. The fragments included unusual electronic components, shattered vacuum tubes, smaller than anything German manufacturers produced, and precision mechanical parts, whose purpose was not immediately apparent. The components were forwarded to the Reichspost research laboratories in Berlin for analysis. Engineers examining the fragments recognized immediately that they were looking at electronics designed to operate inside artillery shells, something German theory suggested was impossible. The vacuum tubes were miniaturized beyond German manufacturing capability, built to tolerances measured in hundredths of millimeters. The mechanical components showed precision machining that exceeded German industrial standards. Most puzzling were components that appeared to be radio frequency oscillators and receivers, suggesting the shell contained a functional radio system. Why would an artillery shell require radio transmission and reception capability? The answer was not immediately obvious, but the implications were deeply troubling. German attempts to develop guided munitions had explored various approaches throughout the war years. The Fritz X guided bomb used radio control, requiring an operator in the launching aircraft to guide the weapon visually onto target. The Henschel HS-293 employed similar principles. Both systems required human operators and worked only when targets remained visible. German engineers had investigated proximity sensing for bombs and rockets, developing acoustic sensors for anti-shipping weapons and infrared sensors for air-to-air missiles. But these systems operated at relatively low speeds and modest acceleration forces. Adapting similar technology for artillery shells that experienced forces hundreds of times greater during launch seemed impossible. The materials, the miniaturization, the ruggedness required exceeded German industrial capability by margins. German engineers thought represented years or decades of development work. Yet the fragments recovered from the Channel suggested Allied engineers had built precisely such devices and deployed them operationally in sufficient numbers to affect battle outcomes measurably. The German scientific community in 1944 was deeply aware of its technological isolation. Contact with international physics and engineering communities had been severed by war. Scientific journals from Britain and America no longer reached German libraries. Conferences where ideas were exchanged and developments discussed had ceased. German researchers worked in intellectual isolation, unaware of breakthroughs occurring in Allied laboratories and unable to benefit from the collaborative exchange that characterizes peacetime scientific progress. This isolation created blind spots where German assumptions about technical feasibility went unchallenged by alternative perspectives. When German engineers calculated that miniaturized electronics could not survive artillery launch forces, no contrary evidence from Allied research existed to suggest their calculations might be incomplete or based on incorrect assumptions about material properties or design approaches. The isolation meant German science was working from a frozen snapshot of pre-war knowledge, extended through internal development, but not informed by the explosive wartime progress occurring in Allied research establishments. By winter 1944, the strategic situation facing Germany had deteriorated catastrophically. The Western Allies had liberated France and were advancing toward the Rhine. In the east, Soviet armies were approaching German borders after years of grinding offensive operations. In Italy, Allied forces had broken through the Gothic Line and were pushing northward. Germany faced enemies on multiple fronts, each possessing material superiority that grew more overwhelming with each passing month. In this context of strategic desperation, Germany launched its final major offensive in the west, Operation Wacht am Rhein, the Battle of the Bulge. The offensive aimed to split Allied armies, capture the port of Antwerp, and force a negotiated settlement in the west. The attack achieved initial surprise and made substantial gains before being halted by determined American resistance and overwhelming Allied material superiority. During the battle and its aftermath, German forces experienced firsthand the devastating effectiveness of Allied proximity-fused ammunition. American artillery supporting defensive positions around Bastogne and elsewhere employed shells that burst above German infantry and armor with lethal effectiveness. Traditional artillery shells detonated upon ground impact, their fragmentation effects diminished by terrain that absorbed blast and shrapnel. Shells with mechanical time fuses could be set to burst at altitude, creating airbursts more effective against exposed infantry, but required accurate ranging and timing calculations that were difficult to achieve against moving targets or in fluid combat situations. The Allied shells seemed to sense their proximity to targets and detonate at optimal height automatically, creating airbursts of devastating effectiveness. German infantry attacking across open ground faced steel hail from shells that burst precisely overhead at heights calculated to maximize fragmentation coverage. The effect on unit cohesion and morale was profound. Soldiers could seek cover from traditional artillery by using terrain features, foxholes, and trenches. Against proximity-fused airbursts, the only protection was overhead cover, substantial enough to stop shell fragments, and even that was less effective than against ground-burst conventional shells. Wehrmacht after-action reports from the Ardennes offensive documented the psychological and tactical impact of facing proximity-fused ammunition. Infantry formations that would normally maintain cohesion under conventional artillery fire broke and scattered under proximity, fused barrages. Officers reported that soldiers feared artillery in ways that traditional fire had not inspired, understanding instinctively that the rounds were more lethal because they exploded with uncanny precision at killing height. Casualty rates from artillery fire increased measurably when proximity fuses were employed compared to traditional time-fused ammunition. Medical units treating wounded noted injury patterns consistent with overhead airbursts, confirming that shells were detonating above troops rather than on ground impact. The tactical advantage proximity fuses provided the Allies was substantial and obvious to anyone experiencing their effects firsthand. This was not marginal improvement in existing technology, but a qualitative change in artillery effectiveness that German forces had no equivalent capability to counter or match. Following the failure of the Ardennes offensive, American forces resumed their advance toward the Rhine in early 1945. German defenders fought with determination despite impossible odds, trading casualties for time as the Reich shrank under pressure from east and west. Artillery exchanges were constant as American forces systematically reduced German defensive positions. On December 17th, 1944, during fighting near Aachen, American artillery conducted a particularly intense bombardment of German positions. Thousands of shells were fired in preparation for an infantry assault. Most functioned as designed, but warfare's chaos ensures that some percentage of any munition fails to perform correctly. In this case, a single American 105mm shell malfunctioned during flight. Instead of detonating at optimal height over its target area, the fuse triggered prematurely while the shell was still several hundred meters in the air. The explosion occurred over German-held territory, and fragments fell among German positions rather than affecting American troops as intended. Wehrmacht ordnance recovery teams, trained to salvage unexploded munitions for intelligence analysis, and in some cases to recover explosives for German use, investigated the detonation site after the bombardment ceased. What they found scattered across the frozen ground was revolutionary, though its significance was not immediately apparent to the soldiers gathering fragments. Among the shell casing pieces and explosive residue were electronic components, tiny vacuum tubes no larger than a child's finger, precision mechanical parts whose purpose was unclear, and a small object that looked like a miniature antenna made of thin wire, formed into a specific pattern. The soldiers recognized they had found something unusual, components that clearly came from inside an artillery shell, yet appeared to be sophisticated electronics rather than simple mechanical fuse mechanisms. The fragments were carefully collected and packaged, then forwarded through Wehrmacht intelligence channels to Heeresversuchsstelle Kummersdorf, the army experimental station south of Berlin. Kummersdorf served as one of Germany's primary ordnance research and testing facilities, where captured enemy equipment was analyzed and German weapons were developed and tested. The facility had examined thousands of pieces of Allied equipment during the war, from small arms to tank components to aircraft systems. Teams of engineers and scientists worked systematically to understand enemy capabilities through careful examination of captured material. The shell fragments arriving from Aachen were assigned to Dr. Heinrich Klein, a radio engineer who specialized in miniaturized electronics. Klein had worked at Kummersdorf since 1941, analyzing captured equipment and attempting to reverse engineer Allied technology. He had examined British radar components, American communications equipment, and Soviet artillery fuses. His expertise in radio frequency circuits and miniaturized vacuum tube technology made him ideally suited to analyze whatever electronic systems the shell fragments represented. When Klein first examined the components laid out on his laboratory bench on December 17th, his initial reaction was professional skepticism. The components appeared to be a radio frequency transmitter and receiver circuit, miniaturized to fit inside an artillery shell. But this seemed impossible based on everything Klein knew about electronic survivability under artillery launch forces. Vacuum tubes shattered when subjected to shock loads far lower than what occurred during shell firing. The acceleration forces inside a gun barrel peaked at 30,000 times Earth's gravity, forces that would instantly destroy any vacuum tube Klein had ever worked with. Yet here were vacuum tubes, clearly designed to operate inside artillery shells, suggesting Allied engineers had solved materials and manufacturing problems German specialists considered insurmountable. Klein began systematic examination of each component, photographing fragments from multiple angles, measuring dimensions with precision calipers, attempting to understand the design principles that made such miniaturization possible. The vacuum tubes were unlike anything in German production. They were tiny, barely 3 centimeters long and 1 centimeter in diameter, yet contained all the elements of a functional tube: cathode, anode, grid structures, and vacuum envelope. The glass was thicker than standard radio tubes, clearly designed to withstand higher mechanical stress. The internal elements were mounted with extraordinary care, using shock-absorbing techniques Klein had never encountered. Small springs held components in place, allowing them to flex under acceleration rather than breaking rigidly. Every aspect of the design showed thoughtful engineering focused on surviving the extreme environment inside an artillery shell. Klein had worked with vacuum tube design throughout his career and recognized immediately that what he was examining represented manufacturing capabilities beyond German industry's reach. The precision required, the materials used, the assembly techniques all indicated production processes refined through extensive development work and scaled to industrial manufacturing volumes. The mechanical components were equally impressive and equally mysterious in their exact function. Klein found gear trains with teeth so fine they required magnification to examine properly, spring mechanisms manufactured to tolerances measured in thousandths of millimeters, a small electric motor no larger than a pencil eraser. Each component was beautifully made, exhibiting precision that exceeded German manufacturing standards. What purpose these mechanisms served was not immediately clear, but their presence inside an artillery shell suggested complexity far beyond traditional time fuses. Klein found what appeared to be a small battery, exhausted now but clearly designed to provide electrical power. The battery was smaller than those used in German flashlights, yet appeared capable of delivering substantial current for short periods. Chemical analysis would later reveal that Allied engineers had developed battery technology significantly more power-dense than German equivalents, another area where Allied capabilities exceeded German assumptions about miniaturization limits. Every component Klein examined told the same story. Allied engineers had achieved levels of miniaturization and ruggedness that German theory suggested were not achievable within wartime development timescales, if achievable at all. Over the following days, Klein worked methodically to reconstruct the shell's electronic system from the fragments. It became clear that the device was a radio proximity fuse, a system that sensed the shell's proximity to targets by transmitting radio waves and detecting reflections from nearby objects. When the reflected signal reached sufficient strength, indicating the shell was near a target, the fuse triggered detonation. The concept was elegant and obvious in retrospect. Radio waves traveled at light speed and could detect objects at distances measured in meters or tens of meters. By continuously transmitting radio pulses and measuring returned echoes, the fuse could determine when it was passing near solid objects like aircraft fuselages or ground vehicles or troop formations. At the optimal moment, when returned, signal strength indicated closest approach to target, the fuse would trigger the shell's explosive charge, detonating at precisely the height and position to maximize effectiveness against the intended target. The principle was similar to radar but miniaturized to fit inside a spinning, accelerating artillery shell and made rugged enough to survive forces that would destroy laboratory equipment instantly. Klein's analysis revealed layer upon layer of sophisticated engineering solutions to problems German researchers had not seriously attempted to solve. The transmitter generated radio frequency energy at approximately 90 MHz, a frequency chosen because it reflected efficiently from metal objects while penetrating weather and battlefield obscuration. The transmitter had to be powerful enough to illuminate targets at useful range, yet compact enough to fit in the limited space available inside a shell fuse cavity. Allied engineers had designed oscillator circuits using miniaturized vacuum tubes that generated sufficient radio frequency power while surviving artillery launch forces. The receiver had to detect extraordinarily weak reflected signals in the presence of noise and interference, extracting target echoes from background clutter. Allied engineers had designed amplifier circuits with gain sufficient to detect signals at microvolt levels, using vacuum tubes whose performance specifications exceeded German manufacturing capability. The discrimination circuit that determined when reflected signal strength indicated target proximity had to operate reliably, despite the shell spinning at hundreds of revolutions per second. Allied engineers had designed mechanical and electronic compensation that made the system function regardless of shell rotation, an achievement Klein recognized as requiring extensive development work and testing. The power supply presented perhaps the most impressive engineering achievement Klein encountered in his analysis. Artillery shells experienced acceleration forces during launch that peaked at 30,000 times Earth's gravity, sustained for milliseconds as the shell traveled down the gun barrel. Any battery had to survive these forces without internal damage, then provide stable electrical current to power transmitter, receiver, and detonation circuits during the shell's flight time of 15 to 30 seconds, depending on trajectory. German battery technology used in portable radios and similar equipment would have been crushed instantly under such acceleration. Internal plates shorting together, electrolyte leaking, connections failing catastrophically. The Allied battery Klein examined, though exhausted and partially damaged by the premature detonation, showed construction techniques that addressed these challenges with elegant simplicity. The battery cells were wound tightly with internal separators that prevented plate movement under acceleration. Electrolyte was absorbed into porous separators rather than existing as free liquid that could slosh and cause shorts. Connections were welded rather than crimped, ensuring mechanical integrity under shock loads. Every aspect of the design reflected deep understanding of the operating environment and careful engineering to ensure reliability under conditions that would destroy conventional components instantly. Klein recognized that developing such a battery required extensive testing programs to validate performance under actual artillery launch conditions. Engineers would need access to test-firing facilities where prototype batteries could be subjected to full artillery acceleration forces, then immediately tested for electrical performance to verify they still functioned correctly. This implied development programs with timelines measured in years and budgets sufficient to support hundreds or thousands of test firings. The Allied proximity fuse program clearly had received priority support at levels German research programs rarely achieved, reflecting strategic decisions to invest heavily in technologies promising substantial battlefield advantages. Klein had worked on German weapons development long enough to understand how resource allocation decisions shaped what technologies could be developed successfully. Programs receiving adequate funding, manufacturing support, and testing resources could overcome technical obstacles through systematic engineering. Programs that were starved for resources or treated as low priority rarely achieved their objectives, regardless of how talented the scientists and engineers working on them might be. The proximity fuse fragments told a story not just of technical achievement but of organizational commitment to developing this specific capability, despite whatever obstacles arose during development. The antenna system demonstrated another layer of sophisticated engineering that impressed Klein deeply, despite his growing understanding that German technology had fallen far behind Allied capabilities in miniaturized electronics. The antenna had to radiate and receive radio frequency energy efficiently while withstanding artillery launch forces and functioning despite the shell spinning at hundreds of revolutions per second. Allied engineers had designed a ring antenna formed from thin wire, shaped into a specific pattern that provided omnidirectional coverage around the shell's axis of rotation. As the shell spun, the antenna pattern rotated with it, but the omnidirectional radiation pattern meant targets could be detected regardless of shell orientation. The antenna was integrated into the fuse body, protected during loading and launch, then deployed or exposed during flight to begin functioning. The mechanical design ensured reliable operation while keeping the antenna compact enough to fit within the shell's aerodynamic envelope. Klein recognized that designing such an antenna required sophisticated understanding of radio frequency propagation, antenna theory, and mechanical engineering. The design had to be validated through extensive testing to ensure it functioned correctly when spinning, when subjected to wind forces during flight, and when exposed to the electromagnetic environment of a battlefield with multiple radio emitters and potential sources of interference. The detonation circuit completed the system, translating detected target proximity into explosive initiation at precisely the right moment. This circuit had to be absolutely reliable, detonating when appropriate but never triggering accidentally due to noise, interference, or component malfunction. Safety requirements for artillery ammunition were stringent. Fuses had to remain safe during transport, storage, loading, and launch, arming only during flight after the shell had traveled sufficient distance from friendly forces. Allied engineers had incorporated multiple safety interlocks, ensuring the fuse could not possibly detonate until the shell had spun up to full rotation rate and had been in flight for a minimum time. These safety mechanisms used centrifugal switches that closed only when rotation exceeded specific thresholds and timing delays that prevented arming until several seconds into flight. Every safety feature had to function reliably while adding minimal complexity to a system already constrained by size and weight limitations. The engineering was masterful, balancing performance requirements against safety imperatives, while maintaining reliability under combat conditions that included temperature extremes, humidity, rough handling, and battlefield electromagnetic interference. Klein's detailed analysis consumed several weeks as he documented every component, every design feature, every engineering solution the Allied fuse incorporated. His report to Wehrmacht ordnance authorities was comprehensive, technically rigorous, and professionally devastating in its conclusions. The Allied proximity fuse represented technological achievement beyond German capability to replicate within any reasonable time frame, given Germany's deteriorating industrial situation and resource constraints. Klein's report, preserved in German archives and later captured, and by Allied intelligence teams after the war, was notable for its unflinching honesty about German limitations. Klein did not attempt to minimize the achievement the fragments represented, or suggest that German engineers could quickly develop equivalent capabilities. He stated plainly that the proximity fuse demonstrated Allied superiority in miniaturized electronics, precision manufacturing, battery technology, and systems engineering. Every aspect of the device showed evidence of extensive development programs, industrial-scale production, and testing validation that German programs could not match. The report's tone was clinical and professional, but its implications were unmistakable to anyone who read it. Germany had been outclassed comprehensively in a technology with profound battlefield implications. The psychological impact of Klein's findings extended beyond the technical community to Wehrmacht leadership already grappling with Germany's deteriorating strategic position. Field commanders who had experienced proximity-fused artillery firsthand needed no technical explanation to understand its effectiveness. They had seen its results in casualty statistics and unit combat effectiveness degradation. But understanding that the technology represented such a profound engineering achievement, something Germany had no prospect of matching, added another dimension to the sense that the war was irretrievably lost. Germany faced enemies with not just numerical superiority, but technological advantages that German industry and science could not overcome. The proximity fuse joined a growing list of Allied capabilities that German forces encountered with no effective counter. Allied air superiority had become absolute, with thousands of aircraft dominating skies over every battlefield. Allied logistics delivered supplies in volumes German transportation networks could never match. Allied industrial production outpaced German manufacturing by ratios that made numerical comparison almost meaningless. Now it was clear that Allied technology in key areas had surpassed German capabilities by margins measured in years of development work. German attempts to understand how the Allies had achieved such advanced miniaturization focused initially on manufacturing techniques and materials science. The vacuum tubes Klein examined used glass compositions that were stronger than German equivalents, able to withstand higher mechanical stress without shattering. Chemical analysis revealed that Allied glass manufacturers had developed formulations with superior mechanical properties, likely through systematic testing of various compositions to optimize strength while maintaining the optical and electrical properties required for vacuum tube envelopes. German glass industry certainly possessed the technical knowledge to develop similar materials given sufficient time and resources, but wartime production pressures had prevented the sort of methodical materials development that peacetime research laboratories could conduct. Allied laboratories had apparently continued materials research programs throughout the war, systematically improving component performance even as production volumes increased to meet military demands. This reflected organizational capabilities and resource allocation that Germany had not matched, treating component improvement as a continuous process rather than freezing designs for production expediency. The internal mounting techniques for vacuum tube elements showed similar evidence of sophisticated development work. Klein noted that Allied engineers had used small coil springs to mount tube elements, allowing them to flex under acceleration rather than braking. The springs were precisely calibrated to provide enough resistance to prevent excessive movement while allowing enough deflection to absorb shock loads. Developing such mounting techniques required understanding the dynamics of components under high acceleration, probably validated through extensive testing, where tubes were subjected to artillery launch forces and then examined to determine which mounting approaches provided best survival rates. German engineers had not pursued such development because they had assumed from the outset that vacuum tubes could not survive artillery launch regardless of mounting techniques. The Allied approach of systematically testing various solutions until finding ones that worked demonstrated a different research philosophy, one that refused to accept theoretical limitations without extensive experimental validation. Klein recognized this as a fundamental difference in engineering culture. German researchers tended toward theoretical analysis that predicted what should or should not be possible, while Allied researchers in this case had pursued experimental programs that discovered what actually was possible despite theoretical obstacles. The miniaturization itself represented industrial capabilities that impressed Klein as much as the technical design. Manufacturing vacuum tubes at the small scale, the proximity fuse required involved processes that demanded precision far exceeding normal production standards. Components had to be assembled inside glass envelopes, barely larger than the components themselves. Connections had to be made reliably, despite working at scales where normal assembly techniques became impractical. Quality control had to ensure that each tube met performance specifications, despite the difficulties of working at such small scales. German vacuum tube industry, among the world's finest before the war, could certainly manufacture miniature tubes given appropriate development time and resources. But scaling such production to volumes sufficient for military applications while maintaining quality standards required industrial organization and manufacturing expertise that took years to develop. Allied industry had apparently begun proximity fuse, a development early enough that manufacturing processes had been refined through production experience, moving beyond laboratory prototypes to reliable industrial production, yielding thousands of units monthly. The strategic implications of the proximity fuse's battlefield deployment troubled German military analysts as much as the technical achievement itself. The Allies were not employing proximity fuses sparingly as exotic special weapons reserved for critical situations. They were using them routinely in regular artillery fire missions, suggesting production volumes in the hundreds of thousands or millions of rounds. This implied industrial commitment to proximity fuse production at scales that diverted significant resources from other munitions programs. The fact that the Allies could afford such diversion could produce proximity-fused shells in such volumes while simultaneously producing conventional ammunition, aircraft, vehicles, ships, and all other war material, demonstrated industrial capacity beyond German comprehension. Germany faced chronic shortages of every resource: ammunition, fuel, raw materials, spare parts, food. Every production decision involved agonizing trade-offs. Increasing output of one item meant decreasing production of something else equally necessary. The Allies apparently faced no such constraints, producing advanced munitions in volumes that would have bankrupted German industrial capacity while maintaining production of everything else needed for global military operations across multiple theaters. Klein's analysis revealed that the proximity fuse had not appeared suddenly in 1944, but had been under development since before American entry into the war. Intelligence pieced together from various sources suggested American research had begun in 1940 or 1941, meaning the fuse represented 3 to 4 years of development before battlefield deployment. This timeline explained the sophistication Klein observed in the fragments. Allied engineers had not rushed a prototype into production, but had systematically developed and refined the technology through multiple iterations. Early prototypes had identified problems that subsequent designs addressed. Manufacturing processes had been developed and validated. Testing had been exhaustive, ensuring reliability before committing to mass production. The development program had received priority support throughout, suggesting strategic leadership recognized the technology's potential value and allocated resources accordingly, despite competing demands from other critical programs. Germany had launched numerous weapons development programs during the war, some successful but many abandoned when they encountered technical obstacles or when resources were diverted to more immediate priorities. The proximity fuse showed what could be achieved when a program received sustained support through inevitable difficulties until technical problems. were solved and reliable production established. The human dimension of the technological gap Klein's analysis revealed was perhaps most troubling to those who understood its implications fully. German scientists and engineers were not inherently less capable than their Allied counterparts. Many had trained at the same universities, studied the same physics and engineering principles, published in the same journals before war severed academic connections. German industry before the war had been among the world's most advanced, producing precision machinery, chemicals, electronics, and manufactured goods that competed globally. Yet, in the specific technologies most critical for modern warfare, radar, proximity fuses, computing devices, advanced aeronautics, Germany had fallen behind by margins that proved decisive. The explanation lay not in individual capability, but in systemic factors, how nations organized their scientific and industrial resources for war, how they prioritized research and development, how they managed the translation of laboratory discoveries into battlefield capabilities. The Allies, particularly the United States, had mobilized science and industry at scales Germany never matched, creating research establishments, employing thousands of scientists and engineers, funding programs with budgets measured in hundreds of millions of dollars, building production facilities specifically for advanced technologies. Germany's scientific establishment in 1945 was a shadow of its pre-war strength, degraded by years of war, losses of personnel, destruction of facilities by Allied bombing, and isolation from international scientific community. Many of Germany's best scientists had emigrated during the 1930s, fleeing Nazi racial policies that made Germany unlivable for Jewish scientists, regardless of their contributions to German science. Those who remained worked under increasingly difficult conditions as the war situation deteriorated. Laboratories lacked basic supplies, electricity was unreliable due to bombing damage, communications were disrupted, and the military situation created constant uncertainty about the future. Research programs were repeatedly disrupted as facilities were evacuated from threatened areas, personnel were conscripted for military service, and resources were diverted to immediate tactical needs. In such circumstances, long-term development programs like those required to create proximity fuses became impossible to sustain, even if German scientists possessed the necessary knowledge and German industry retained the manufacturing capability. The proximity fuse story illustrated that technological advantage in warfare required not just scientific knowledge, but stable institutional frameworks that could sustain development programs through years of work despite setbacks and competing pressures. Klein's report circulated among Wehrmacht ordnance specialists and reached some members of German military leadership, though by early 1945 the strategic situation had deteriorated so catastrophically that technological assessments of enemy capabilities seemed almost academic exercises. Soviet armies were advancing into Germany from the east, American and British forces were crossing the Rhine in the west, and Germany's cities were being systematically destroyed by round-the-clock bombing. Whether German artillery possessed proximity fuses or not would not change the war's outcome at this stage, though the knowledge that such technological gaps existed added another layer to the sense of inevitable defeat. For the scientists and engineers who read Klein's analysis, the proximity fuse represented professional recognition that their Allied counterparts had achieved something genuinely impressive, solving problems German specialists had considered insurmountable, and deploying the resulting technology at industrial scale. There was no shame in acknowledging a superior achievement when it was demonstrated so conclusively. The proximity fuse fragments Klein examined were evidence of engineering excellence that deserved professional respect regardless of wartime allegiances. The full story of Allied proximity fuse development, which Klein and his colleagues could only partially reconstruct from intelligence fragments and captured equipment, represented one of the war's most successful secret weapons programs. The effort had begun in the United States in 1940, initiated by the National Defense Research Committee under Vannevar Bush. Bush, a former MIT dean and one of America's preeminent science administrators, understood that modern warfare would be decided as much in laboratories as on battlefields. He convinced President Roosevelt to establish organizations that could mobilize American scientific talent for weapons development, creating institutional frameworks that would prove extraordinarily effective at translating scientific knowledge into military capabilities. The Proximity Fuse program, designated Variable Time or VT Fuse for security purposes, received priority support from its inception. Bush recognized that anti-aircraft effectiveness represented a critical vulnerability for Allied forces. Existing mechanical time fuses required skilled operators and achieved hit rates measured in fractions of 1%, even under optimal conditions. An automatic fuse that could sense target proximity and detonate at optimal range would revolutionize anti-aircraft effectiveness and provide advantages in other applications, including surface bombardment and anti-personnel, artillery fire. The technical challenges were formidable and obvious to anyone familiar with artillery and electronics. A proximity fuse had to survive artillery launch forces that peaked at 30,000 times Earth's gravity, function while spinning at hundreds of revolutions per second, operate reliably in temperature extremes from Arctic cold to tropical heat, resist moisture that could corrode components or cause electrical failures, and provide power to radio circuits from compact batteries surviving the same acceleration forces. Each requirement represented significant engineering challenges. Together, they seemed almost insurmountable, which explains why German engineers had concluded such devices were impractical for artillery applications, despite understanding the underlying principles. American researchers approached the challenges systematically, breaking the overall problem into specific technical requirements that could be addressed through focused development programs. Vacuum tube survivability became one research effort. Battery development became another. Radio frequency circuit design, antenna engineering, safety mechanisms, detonation circuits, each aspect of the complete system became a separate project with dedicated teams working toward specific performance goals. This organizational approach allowed parallel development where solutions to individual problems proceeded simultaneously, converging toward complete system integration as components matured. The vacuum tube development program illustrated how systematic engineering could overcome obstacles that seemed insurmountable when viewed holistically. Researchers at the National Bureau of Standards, working with industry partners including Sylvania, Raytheon, and other vacuum tube manufacturers, began testing commercial tubes under simulated artillery launch forces. Predictably, standard radio tubes shattered instantly when subjected to acceleration forces approaching those experienced during shell firing. Rather than concluding tubes could not survive such forces, researchers analyzed failure modes to understand why tubes broke and how designs might be modified to prevent failures. They discovered that glass envelopes fractured along stress points where internal supports created pressure concentrations. Tube elements broke at connection points where mounting techniques allowed excessive movement under acceleration. Filaments snapped when unsupported lengths vibrated at resonant frequencies excited by launch forces. Each failure mode suggested design modifications that might prevent or mitigate the problem. Researchers systematically tested variations, thicker glass envelopes, different mounting approaches, spring supports that allowed flexing rather than rigid mounting, shorter unsupported element lengths, and alternative connection techniques. Through hundreds of tests over months of development, they identified designs that survived artillery launch with acceptable reliability. The miniaturization requirement drove another parallel development effort. Standard radio tubes were far too large to fit inside artillery fuse cavities that measured only a few centimeters in each dimension. Researchers had to design tubes that retained necessary electrical characteristics while shrinking to perhaps 1/4 the volume of comparable commercial tubes. This required rethinking every aspect of tube construction. Electrodes had to be smaller while maintaining required surface areas. Spacing between elements had to be reduced while preventing electrical breakdown. Glass envelopes had to be thinner to reduce weight while remaining strong enough to survive launch forces. Assembly techniques had to work at scales where standard manufacturing methods became impractical. The development program moved systematically through prototype iterations, each generation incorporating lessons learned from testing previous versions. By 1942, manufacturers were producing miniature ruggedized vacuum tubes that met all performance requirements, surviving artillery launch forces, operating reliably over temperature ranges from -40 to +70 degrees Celsius, and maintaining electrical specifications within acceptable tolerances, despite manufacturing variations inherent in any production process. The tubes were more expensive than standard commercial tubes and required specialized manufacturing techniques, but they worked reliably, which was the essential requirement for military applications where cost was secondary to performance. Battery development followed similar methodical approaches. Standard batteries used in flashlights and portable radios would be destroyed instantly by artillery launch forces, internal plates shorting together, cases rupturing, electrolyte leaking. Researchers at the National Bureau of Standards and industry partners, including Burgess Battery Company, developed batteries specifically designed for proximity fuse applications. They tested various cell constructions, identifying designs where plates were wound tightly enough to prevent movement under acceleration, where electrolyte was absorbed into separators rather than existing as free liquid, where cases were strong enough to contain internal pressures generated during launch, and where electrical connections remained intact despite mechanical forces trying to tear them apart. The batteries had to provide sufficient current to power radio circuits, while remaining small enough to fit in fuse bodies alongside all other components. They had to activate reliably when required, remain safe during storage and handling, and function across temperature ranges encountered in military operations from Arctic to tropical environments. Development required thousands of test firings where prototype batteries were subjected to actual artillery launch forces and then immediately tested to verify electrical performance. By 1942, manufacturers had validated battery designs that met all requirements, enabling proximity fuses to carry their own power supplies, rather than depending on external power sources that were impractical for artillery applications. The radio frequency circuits required sophisticated design work that pushed the boundaries of 1940s electronics engineering. The transmitter had to generate radio frequency signals at approximately 90 MHz, with sufficient power to illuminate targets at ranges of tens of meters, while fitting inside the constrained fuse volume. Oscillator circuits had to operate stably despite spinning at hundreds of revolutions per second and temperature variations during flight. The receiver had to detect extraordinarily weak reflected signals, amplifying them sufficiently for processing by detonation circuits, while rejecting noise and interference from other radio sources. Allied engineers designed circuits using the miniature ruggedized vacuum tubes developed specifically for proximity fuse applications, optimizing performance within the constraints of available components and space limitations. The circuits were tested exhaustively under conditions simulating operational environments, verifying they functioned correctly when spinning rapidly, when subjected to vibration and acceleration forces, and when exposed to electromagnetic interference from other radio transmitters. By 1943, circuit designs had been validated and optimized for reliable production, with manufacturing processes ensuring consistent performance across production batches. The mechanical design of complete fuses integrated all components into assemblies that could be manufactured at industrial scale while maintaining reliability under combat conditions. Fuse bodies had to protect internal components during storage, transport, and loading, while allowing radio frequency transmission and reception during flight. Safety mechanisms had to prevent accidental detonation while ensuring reliable arming after launch when fuses were far enough from friendly forces. Detonation circuits had to trigger explosives at precisely the correct moment when reflected signal strength indicated optimal target proximity. Every mechanical component required precision manufacturing to tolerances measured in hundredths of millimeters, far exceeding normal production standards for artillery ammunition. American industry rose to these challenges through systematic application of quality control methods and manufacturing process improvements. Companies including Eastman Kodak, Wurlitzer, and others not traditionally associated with electronics manufacturing were brought into production programs, receiving technical support and tooling to manufacture components meeting exacting specifications. By mid-1943, multiple manufacturers were producing proximity fuses at rates approaching hundreds of thousands monthly, transforming exotic technology into commodity items available in quantities sufficient for routine battlefield use. The testing program that validated proximity fuse reliability before battlefield deployment was extraordinarily comprehensive, reflecting American determination to ensure the weapons would perform as designed under actual combat conditions. Test firings were conducted at Aberdeen Proving Ground and other facilities where fuses could be fired under controlled conditions and their performance measured precisely. Fuses were tested against various target types, including aircraft, ground vehicles, and personnel, verifying detonation occurred at optimal ranges. Environmental testing subjected fuses to temperature extremes, humidity, vibration, rough handling, and storage under various conditions to ensure reliability throughout logistics chains from factory to battlefield. Safety testing verified that fuses remained safe during handling and would not detonate accidentally despite mishandling, drops, or exposure to fire. By the time proximity fuses entered combat use, they had been tested more thoroughly than perhaps any other munition in military history, giving commanders confidence they would perform reliably when needed. This level of testing required enormous investments of time, resources, and ammunition, but it ensured that the final product worked correctly, avoiding the waste that would result from deploying unreliable equipment that failed in combat after enormous production investments. Security surrounding proximity fuse technology was extraordinarily tight, reflecting Allied recognition that the weapons represented decisive technological advantage that would be compromised if enemies understood their operating principles and developed countermeasures. Fuses were initially restricted to use over water or in situations where recovery by enemies was unlikely. Shells fired over land were prohibited except in circumstances where battlefield situation ensured enemy forces could not recover duds or fragments for analysis. These restrictions relaxed gradually as production increased and as intelligence assessments concluded that Germany and Japan lacked capability to develop equivalent technologies even if they understood Allied operating principles. By the Battle of the Bulge in December 1944, proximity fuses were being used routinely in ground combat without restrictions, suggesting Allied confidence that technological superiority was secure, regardless of whether enemies captured samples for analysis. This assessment proved correct. Despite German recovery of proximity fused shells and detailed analysis by scientists like Klein, Germany never developed equivalent capabilities before war's end. The battlefield impact of proximity fuses was measurable and substantial across multiple applications. Against aircraft, proximity-fused anti-aircraft shells increased effectiveness by factors of 3 to 5 compared to conventional time-fused ammunition, meaning gunners achieved the same number of kills using 1/3 to 1/5 as much ammunition. Against Japanese kamikaze attacks in the Pacific, proximity-fused shells provided the only effective defense against massed suicide aircraft attacking naval vessels. Ships, equipped with proximity-fused ammunition, survived attacks that would have overwhelmed defenses using conventional ammunition. In ground combat, proximity-fused artillery provided devastating effectiveness against exposed infantry and soft targets. Shells bursting at optimal height above ground created fragmentation patterns far more lethal than ground-burst conventional rounds. Infantry caught in open terrain faced steel hail from above, with no effective cover except thick overhead protection that was rarely available on fluid battlefields. The psychological effect was profound. Soldiers feared proximity, fused artillery more than conventional fire, because they understood instinctively that overhead bursts were more lethal and that their normal protective measures were less effective. The strategic implications extended beyond immediate tactical advantages. Proximity fuses represented American capability to mobilize science and industry for weapons development at scales exceeding anything enemies could match. The program cost approximately $30 million, employed thousands of scientists and engineers, involved dozens of companies in production networks, and delivered millions of fuses that gave Allied forces decisive advantages in multiple combat environments. This demonstrated institutional capabilities for technology development that would shape post-war military competition. The proximity fuse program became a model for how nations could organize scientific research and industrial production to create advanced weapons, influencing post-war military research and development approaches that characterized the Cold War era. The success validated Vannevar Bush's vision of mobilizing science for national security, leading directly to post-war establishment of permanent research institutions, including what would become the Defense Advanced Research Projects Agency and other organizations that would drive military technology development for decades. For Germany, the proximity fuse joined a catalogue of Allied technological achievements that German forces encountered with no effective countermeasures. Superior Allied radar had given British and American forces decisive advantages in detection and fire control. Allied code-breaking had compromised German military communications throughout the war. Allied computing capabilities had enabled calculations supporting operations planning, logistics, and weapons development at scales. German capabilities could not match. Each technology represented areas where Allied institutional capabilities, organizational approaches, and resource commitments had produced results that Germany could observe but not duplicate within timeframes that mattered strategically. The pattern was clear to those willing to see it honestly. Germany had lost the technological competition that ran parallel to military campaigns, a defeat as consequential as battlefield reversals because it meant that even tactical successes could not overcome the cumulative weight of Allied material and technological superiority. Klein's report on the proximity fuse was one data point among many, but it illustrated the broader reality with particular clarity, because the technology was so obviously superior and so clearly beyond German capability to replicate, given circumstances of early 1945. The war ended in May 1945 with Germany's unconditional surrender, Allied armies having overrun German territory from multiple directions, making continued resistance pointless. In the aftermath, Allied intelligence teams systematically documented German weapons programs, scientific research, and industrial capabilities. Teams interviewed scientists and engineers, including Klein and others who had analyzed captured Allied equipment. They examined German research facilities, reviewed documentation, and assessed how close Germany had come to developing various advanced weapons. The assessments found that German proximity fuse research had never progressed beyond preliminary theoretical studies. Unlike radar, where Germany had developed operational systems but had fallen behind in specific frequency ranges, or jet aircraft, where Germany had actually achieved limited operational deployment before the Allies, proximity fuses represented technology that Germany had not seriously pursued. German researchers understood the principles, had discussed possibilities theoretically, but had concluded that practical implementation was too difficult given technical obstacles, and had prioritized other development programs. This meant that when Germany finally encountered Allied proximity fuses in combat, they faced not just superior versions of technology they were developing, but completely mature systems that Germany had never attempted to create. The human cost of technological inferiority was measured in casualties that might have been prevented had Germany possessed equivalent capabilities or effective countermeasures. Every soldier killed by proximity-fused artillery, every aircraft shot down by proximity-fused anti-aircraft fire, represented the price of technological decisions made years earlier when research priorities were established and resources allocated. German soldiers faced weapons they could not effectively counter because German scientists and engineers had not developed equivalent technologies or defenses against them. This was not because German scientists were less intelligent or less capable, but because institutional decisions about research priorities, resource allocation, and development timelines had led Germany down different technological paths. By the time Germany recognized what they had missed, circumstances made it impossible to catch up. The decade gap Klein referenced in his analysis was not precisely a decade in calendar terms, but represented the reality that Germany in 1945 possessed capabilities matching Allied technology from earlier in the war, or before, a lag that proved strategically decisive across multiple technologies and applications. The proximity fuse was perhaps the most dramatic example because German research had not even seriously attempted to develop such weapons, meaning the gap was effectively infinite until Germany examined captured examples and understood what they had missed entirely. Up next, you've got two more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.